Okay, we have another example taking products of vectors here. This time we're going to be doing the cross product between two vectors. And I've just chosen these simple prototype vectors here, 2, 3, 4, 5, 6, 7, just so we can see the basic structure. The way that I learned to compute cross products when I was a student was to use this determinant form. So hopefully you went over this in the previous part of the course, but the idea is that we build our determinant up like this. So we got our I, j, and k vectors at the top there. And then we put in the components of our first vector, so that's 2, 3, 4, and then the components of our third vector, 5, 6, 7. So basically, this is a matrix which we build from the components of our vectors, and then we take the determinant of that matrix. That's what the straight lines mean here. And the determinant of a 3 by 3 matrix is written in the following way. So we take each of our top row, and each of them gets a sign as follows. So you get plus, minus, plus for a 3 by 3 matrix. So we get I, our first element, times the determinant of the matrix that's left when we cover the corresponding column and row of I. So if I cover up this column and this row, I'm left with this matrix, the 3, 4, 6, 7. So it's the determinant of the 2 by 2 matrix, 3, 4, 6, 7. Then I do the same thing here, so I'm going to get minus j times the determinant of the 2 by 2 matrix, which is left by crossing up or covering over this top row and this column. So that's going to be the matrix 2, 4, 5, 7. And then plus k, and again, our remaining matrix here is this one, 2, 3, 5, 6. So it's the determinant of 2, 3, 5, 6. And then for a 2 by 2, the determinant is just you take the product of the diagonal elements and you subtract the product of these off diagonal elements. So this is going to be equal to I times, well, 3 times 7 minus, well, we'll multiply, we'll write it out for fullness sake. So 3 times 7 minus 4 times 6, and I'll have minus j, and I'll have 2 times 7 minus 4 times 5, and then plus k, and it'll be 2 times 6 minus 5 times 3. And if I just do those sums then, so 21 minus 24, so that's going to be minus 3i. This will be 14 minus 20, so that's minus 6. But I've got a minus sign here, so it's going to be plus 6j. And here I'm going to have 12 minus 15, so that's minus 3k. And this is the result of our cross product. So A cross B is equal to this thing. Now, that might seem a little long-winded or whatever, and again, we haven't really seen the kind of the point of these cross products, but it will become important when we do rotation, because it turns out cross products are necessary for that. But just one final step here: we've computed A cross B. We've said that the magnitude of the cross product should be equal to the magnitude of A times the magnitude of B times the sine of the angle in between them. We're not going to verify that part. I mean, you can if you want, but you need to work out what the angle is between these two vectors, first of all, and that's a bit long-winded. But we've also said that the direction of this vector, it should be perpendicular to the plane containing A and B. So this vector should be perpendicular to both A and B. The way we can verify that is by taking the dot product. If you remember the key concept about the dot product, it's that the dot product measures how aligned two vectors are. So if the angle in between the two vectors is 90 degrees, then the dot product between them should be 0. So we can verify, I'll just do it for one here. We'll take the dot product between A and this A cross B. So A is just the vector 2, 3, 4, 2i plus 3j plus 4k. And our A cross B is this vector minus 3i, don't need that bracket, minus 3i plus 6j minus 3k. And I'm going to write the dot product in the column form, which I introduced in the previous video, just for simplicity. So the dot product between these two vectors is expressed in this way. I maybe should have written what that is, so hold on a second. Let's move that over. So this is A dot A cross B. Okay, and so when I multiply this out, well, these top two, so 2 times minus 3 will give me minus 6. 3 times 6 will give me plus 18. And 4 times minus 3 will give me minus 12. And right enough, if I take minus 6 minus 12, that's minus 18. This whole thing is equal to 0. So what we verified then is that these two vectors, this A vector here and the vector represented by A cross B, they are indeed perpendicular. And we could do the same thing for the vector B, just to verify that this is also perpendicular to this vector. That's the point of the cross product, is it gives us some vector which is perpendicular to the two vectors that we started with.